Some functions have limits that fail to exist. We know how to recognize when a function is approaching a limiting value using a table, but what would it look like for a function that doesn't approach a certain value? This is an example here. The limit that we're looking at has x approaching 0, so I've created two tables. One where x is approaching 0 from the left, that's the negative numbers that we see, and then one table where we're approaching x equals 0 from the right. That's this table that we see. We're going to plug each of these x values into our function, and you can confirm all of the numbers by typing them into your calculator or using GeoGebra. But I'll fill in the table here for you, and these are the values that come out. So just looking at the left side, all of the negative x values, the numbers are kind of jumping all over the place. So remember that we're getting closer and closer to x equals 0 as we move down the table. So these numbers should be getting closer and closer to this number, but that is not happening. We're not far from each of these points. They're all very close together, but these numbers are jumping all over the place from 0.5 to negative 0.08 to positive 0.3. We call this like an oscillation, where things are jumping all over the place like this. So let's look to the right side of x equals 0 and see if we have anything hopeful over here. Well, in fact, we have very similar numbers, but the minuses have been swapped, and that's a property of the sine function. And as we see again, the numbers are jumping all over the place. There's no pattern that we can follow. So again, we have some oscillation. In fact, this function, sine of 1 over x, if we go to graph it, we can type in f of x equals sine of 1 over x, and we see this wild thing happening near the origin. So let's zoom in and take a look at what's going on. We get more details as we zoom in, but we see what we're going to call uncontrollable oscillation. The function is whipping back and forth uncontrollably. It never settles on a set output value. Therefore, this function does not have a limit that exists. We will show definitions that are a little more rigorous than this, but for now, if we have a table of values where the numbers don't follow a trend, we would determine that the limit does not exist. Now, in looking at that last function where the limit did not exist, we used this idea of a one-sided limit. We looked on the left of our x value, tried to see if we could find a pattern, and then we switched over and looked on the right to see if we have a pattern. This is what we call one-sided limits. Let's talk a little bit more about that. On the screen, I have that bluish purple function from the beginning of the section, and again, it is undefined at x equals 2. But we want to know, can we determine the limit of that function as we're approaching 2? So we'll start with the left-sided limit. I'm going to walk along the function to the left of 2, and I'm going to walk towards the value x equals 2. So I'm getting closer and closer to x equals 2, and I notice that the y values are all at the same. It looks like we're heading towards x equals 1. So we could say that the limit from the left is approaching negative 1. Now, if we switch and start talking about coming from the right, then I'm going to pick x values that are on the right side of x equals 2, and then I'm going to start zooming in towards x equals 2. Now, on this side of the function, looks like we're heading towards positive 1. So from the right, we would say that the limit is approaching positive 1 as x goes to 2. We've got a little bit of new notation that I want to point out here. In our limit notation, we see this minus. It almost looks like an exponent on the 2, but that minus is telling you that we are approaching 2 from the left. And in the second notation at the bottom, I have a little plus sign. It almost looks like an exponent. That plus sign says that we're approaching 2 from the right. Now before, when we wrote these limit notations, we didn't have the plus or the minus. So the absence of a plus or a minus tells you that we're looking at the limit from both sides. But if we do have a plus or a minus, then we're looking at a limit from one side. One-sided limits are particularly useful for piecewise functions. So we have a piecewise function at the top of the screen called f of x. It's made up of 2 separate definitions, and the definitions meet up at the x equals 2. So if we pick x values that are smaller than 2, we need to use the x plus 1 portion of this piecewise. If we use x values that are larger than 2, we need to use x squared minus 4 to define our function. So when we go to generate our table, remember that when we subtract these tiny increments, we're to the left of that 2, which means this function is going to use the x plus 1 to complete the table. The right table, we're adding small increments. Those are going to be larger than 2. So we're going to use x squared minus 4 to complete this table. Go ahead and complete your own table. I have mine filled in already. And this way we can answer the questions for each of the limits. For the left-sided limit, when x is approaching 2 from the left, I can see that we're zooming in on the value, getting closer and closer, 2.9, 2.99, add another 9, add another 9. Eventually, this is going to land on 3. So this limit, as x approaches 2 from the left, the function f of x is approaching the value 3. Now, because this is a piecewise, and we're looking at the piecewise right where it splits, the next table, coming from the right, might look totally different. And sure enough, it does. As we're approaching 2 from the right side, our numbers are getting very, very close to 0. So the limit as x is approaching 2 from the right of the function f of x is narrowing in on the value 0. So one-sided limits don't always equal the same value, especially if we're looking at a piecewise function. I've gone ahead and graphed that piecewise function for you just so that we can get an idea of why we just saw what we saw. Now, x equals 2 is happening right around this x equals 2 line. And if we are traveling on the function to the left of x equals 2, then we're on the red portion of this line. And as we get closer and closer to x equals 2, we are approaching the output of 3. If we were, however, looking at the right-sided limit, we'd be on the blue line. We're approaching x from the right, and that value is approaching 0. So this piecewise function is taking us in 2 completely different places, and we're using one-sided limits to see that. Now that we know what a one-sided limit is, and we know what a two-sided limit is, we can make a connection between them. If we have a function f, that of course is defined on an open interval, you're going to see that written over and over again, but that's just to make sure that we're talking about something that actually exists. So if we're talking about a function f, that's defined everywhere, and we calculate the left-sided limit to equal L, and we calculate the right-sided limit to equal L, well then that tells us that the two-sided limit has to also be equal to L. And vice versa. If we're able to do that two-sided limit, then we know that the left and the right-sided limits have to match. So in the example where we made the left and the right-sided limits and they did not match, well then when it comes time to talk about the two-sided limit, so when we're talking about x approaching 2 from both sides, so I'm not going to put a plus here, I'm not going to put a minus there, I'm going to leave it blank to say I'm approaching from both sides. If I'm looking at that piecewise function that we just saw the graph of, we would have to say that this two-sided limit does not exist. And that's because the left-sided limit was equal to 3, and the right-sided limit was equal to 0. Since these bad boys don't match, the two-sided limit cannot exist. When they do match, then they're equal to the two-sided limit as well. All three of them go together. So they either all match, or these two are different, and the two-sided limit can't exist.